Section 10.2 is dealing with iteration, and what I'm going to do is I'm going to run through how to do the questions first of all. We're not going to worry about why this method works, we're going to just run through how to do it, and then I'll go back and we'll think about why that works. If you know this method, you might want to skip forward until the point where we get to why it works. So, the point of iteration is, if we've got an equation that we can't solve algebraically, so example 5 here looks got a cubic. Let's have a look at some of the examples in the exercises. We've got square roots flying around. Oh, actually, no, that one starts from, there we go. Here's a good example. Question 4. We've got an x, e to the minus x plus 2. If you want to find the roots of that function, that would be the solutions to the equation 0 equals x e to the minus x plus 2. And we don't have a algebraic way of solving that simply. And if you are looking at these equations and, maybe I've missed something, maybe actually there's something perfectly sensible we can do, it's very easy to solve that equation. Well, just imagine an equation that we couldn't solve. That's the purpose of this. If we can't solve the equation, this method will give us a numerical solution. So it won't really solve the equation. It will only give us one solution. Maybe there are going to be several solutions to the equation that we're looking at. And it won't give us an exact answer, it will give us a numerical solution, which means as many decimal places as we want. So if we want 5 decimal places, we can use iteration to get a 5 decimal place solution. So it's not perfect, but firstly, it's useful if what you want is to know where the root is. So if you're an engineer or a physicist and you don't really care about the structure of the mathematics, all you want to know is what is the value of the solution to this equation, then a numerical method will work perfectly well for you and it'll give you an answer as accurate as you need it. And secondly, if you are a mathematician, you're trying to find out something about the structure of the equations and find out an algebraic way of solving these things, then it will still help because it'll give us an idea of where the roots are, and maybe we can then use that information to spot a pattern and develop a method. Okay, that's the idea. When we're using iteration then, we're going to start with example 4. And if you look at this, this is a function that we're perfectly familiar with. And if I'm trying to find the roots of this function, I'm trying to solve the equation 0 equals x squared minus 4x plus 1. And that's an equation that, of course, we can solve, right? It's a quadratic. But we're going to solve it with the iteration method. So, as often in maths, if we've got a new method, we'll pick an easy example first and use it to study the method. In real life, there'd be no need to solve a quadratic using iteration, but it's an example, okay? So, first, so this is where I go into how we do this without explaining why any of these steps work, first of all. First thing we're going to do is we're going to rearrange this and get x on its own on one side. And there are several different ways of doing that. The one they've asked for is to show that we can rearrange it into this form. Well, we can do that by taking the minus 4x and the 1 over the other side. So x squared equals 4x minus 1. I've taken those two over the left-hand side, but then I've swapped left-hand side and right-hand side around. And then if I divide by x on both sides, I get x equals 4 minus 1 over x. Okay? So that's what we were asked to show. And the key features of this equation are that there's an x on its own here, and then there's some expression to do with x on this side, which we can calculate. Okay? So if you gave me x, I'd be able to calculate this expression. In this case, we've only got one x on this side. Could be more than one x over here, and that's fine as well. That's stage 1. Stage 2, we're going to turn that into an iterative formula, and an iterative formula looks just like a recurrence relation. And if you don't remember recurrence relations, it might be worth going back and just reminding yourself, because this notation is a bit unusual if you've not seen it or if you've forgotten it. So it works like this. Now, the way it works is if you tell me a starting point, and in this case we're going to take as a starting point x equals 3, then we're going to say x0 is 3. So x1 is 4 minus 1 over x0, okay? So if n equals 0, this is x0 and this thing here is x1. So the next thing after x0 is x1, and that comes from 4 minus 1 over 3. And then x2, well, if this is a 1, this is a 2, so x2 is calculated by 4 minus 1 over x1, and x3 is calculated by 4 minus 1 over x2 and so on. Okay, so we're going to take the starting value and put it into this expression. Whatever the output is that we get, we're going to put it back into this expression, and then whatever the output is we get, we're going to put it back into this expression. Now you might be seeing here that this is doing the same thing over and over again, and if you're doing the same calculations over and over again, a really good way of doing that is to get a computer or a calculator to do it for you, and I'm sure you can look at quite quickly a good way of putting these into your graphical calculator. I'm not going to try and cover that in these videos, there's too many different kinds of calculators that people use, but I'm sure you can find one for your model very easily. I'm just going to cover the process that we need to go through. So this is what we do, and if we look in the book, this is what we get. We get x1 equals 4 minus 1 over x0, which is this. x2 is 4 minus 1 over x1, which is this, and then this. And if you keep doing that, what you find is that these numbers get closer and closer to the same thing, right? So 3.6, 3.6 recurring, 3.7272, 3.731, and then the next number might be something like 3.731, and then maybe it's starting to change in the 4th and 5th decimal places. And in only a few steps, you'll find that these numbers are going to be the same to as many decimal places as you need. If you stick this in the spreadsheet and just copy the formula down, you'll find that you'll quite quickly get accurate enough that you know it won't fit in the cell. You'll get 7 or 8 decimal places all matching. And that is the solution to our equation. That number that we get is the root of the equation, well, it's the root of this equation, which is the root of this equation as well, because this one is just a rearrangement of the other. So the root of this equation comes from the number that this sequence gets closer and closer to, i.e. the number that this sequence converges to, or the limit of this sequence, if you like, okay? Something I haven't mentioned is where's our starting point then? Why do we pick x equals 3? Well, you need to start somewhere close to the root. Well, how do you find somewhere close to the root? We're trying to find the root. How do we find somewhere close? Well, this is where our sign change method comes in handy for the first time. It's between 3 and 4. We know it's between 3 and 4 because the question asks us to check f of 3 and f of 4 and show that there is a root between 3 and 4 by using the sign change method from section 10.1. So we do the sign change method and find somewhere close to the root, pick a starting point close to the root, anything between 3 and 4 will do. In the question they ask us to use 3, and then repeatedly put that, put the number into the expression, put the answer to the first iteration of the expression, do the next iteration. By the way, iteration, I haven't said, it's just a word that means doing the same thing again and again. So each iteration, this is the first iteration, the second iteration, the third iteration, and so on. And then we end up with numbers that match each other to several decimal places, and that will give us the answer. Now I should say, so let's say we've done this and all our answers to the question might ask us for 2 decimal places, find the answer to 2 decimal places, and if it does, we might end up with 3.73, but it wouldn't be good enough to just say, well, the last 3 iterations have all given us 3.73 to 2 decimal places. The safest thing to do on an exam would be to do this, to say, well, we think the answer is 3.73, so we'll prove it. We'll do f of 3.725, and we'll do f of 3.735, and we'll check that there's a sign change in there, okay? Now, the reason for that is because these numerical methods sometimes do funny things, and it's just going to be because we're going to give you an idea of why it works, but not all the details. You're going to need to make sure that you do the sign change to check that there is definitely a root in that interval. Okay? So that is how we do iteration, and we were at nearly 10 minutes, so I will do a separate video on why iteration works.